Conceptual Introduction to Linear Regression, Part 3, R squared. The most important piece of information that we get from a regression model for psychological data analysis is almost always simply the slope. But sometimes people talk about the R squared value too, so I want you to understand what that is. Once we've fit an ordinary least squares regression model, we've picked a line that minimizes the sum of squared residuals. That sum of squared residuals, the thing that we got as low as it can go without bending the line, comes in handy for various calculations. And one of the things that it helps us calculate is something called R squared. But first, a quick detour. Just a reminder of what mean and variance are for a sample of observations, like our response variable y. The mean is the sum of the values divided by the sample size, and we sometimes write it by putting a bar over the variable. Y bar is the sum of all y values divided by n. The sample variance is what you get by measuring how far each value is from the mean, squaring that distance, adding them all up, and then dividing by the sample size minus 1. In other words, it's the sum of squared deviations from the mean divided by n minus 1. So when we do regression, we get a sum of squared residuals, squared distances from the regression line, and when we calculate variance, we start with a sum of squared deviations from the mean, squared distances from the mean of the sample. These processes are analogous. The sum of squared deviations from the mean is what you would get as the sum of squared residuals if you forced your regression line to be perfectly horizontal, because then you would get a horizontal line at the mean, and all the residuals would just be deviations from the mean. But we did least squares regression with this similarity variable as the predictor. We picked a slope that allowed our line to fit better than that. That was the whole point of picking a slope that minimized the sum of squared residuals. Therefore, the actual sum of squared residuals from our regression line, shown on the right, is always lower than the sum of squared deviations from the mean. So what if you took their ratio? What if you divided the sum of squared residuals by the sum of squared deviations from the mean? This would represent something like a portion of unexplained variance. How much of the original variance remained unexplained, remained residuals, even after you perfected the slope of the line so as to minimize the sum of squared residuals. And 1 minus this ratio is the portion of variance that was explained by the regression model. The residuals are just the differences between the actual values of y and the fitted values from the regression equation. So the numerator and the denominator of this ratio have a similar structure. They are both about how far off some estimates of y are. Another word for R squared is the coefficient of determination, but we normally call this portion of variance explained R squared because for models with one predictor, it is equal to the correlation coefficient squared. And the correlation coefficient, you may recall, is typically symbolized with R. As you add more predictors to your regression model, the sum of squared residuals gets smaller and smaller. This has to happen because we are always minimizing the sum of squared residuals. And so adding more ways to do that can only help, never hurt. Therefore, R squared always goes up as the model gets more complex. It's impossible to add a predictor and explain less variance as a result. So we have something called adjusted R squared, which includes a penalty for complexity. Adding a predictor that explains almost nothing will improve the R squared, but not the adjusted R squared. Therefore, adjusted R squared is better for many kinds of model comparison.